Here is one of my favorite formulas. Rate times time is equal to distance, or RT is equal to D. And I stated in a previous lesson that I rarely use the letter T as a variable because it looks like an addition symbol. But when I'm dealing with this formula, I do use the letter T, and I just try to write neatly. Well, we're going to examine several types of rate, time, and distance problems. There are many. We're going to look at 3 today. And here's one. 2 objects are coming towards one another, and in this case, the objects are airplanes. The first plane has a rate and a time, and the second plane has possibly a different rate and time. And the 2 arrows combined is the original distance that the 2 planes were apart. And the place where the arrows come together is the place where they pass. And in problems like this, we might be asked, how long will it take before the planes pass one another? Or how far apart were they originally? Here's another type of problem. We have 2 trains, and they're leaving a station in opposite directions. So the first train goes to the east with a rate and a time. The second train goes to the west with a different rate and time, perhaps. Sometimes the rates are the same, sometimes the times are the same, but we don't know until we've read the problem. And in this case, at some point in time, they'll be a big distance apart, and that's often what the problem was about, or it might be how long will it take before they get a certain distance apart. But the blue arrow plus the red arrow represents the distance they are apart at a given point in time. And here's a third type of problem. We have 2 cars, and they're leaving from the same place going in the same direction. One car starts first, so it has a rate and time. And the other car waits a bit and starts later, and its job is to catch up. So its time will be less, but its rate will be more, so that the second car can catch up to the first car. And of course, since it's a catch-up problem, their distances will be the same. Well, let's take a look at a problem. 2 planes are traveling toward each other and are 1,330 miles apart. One plane is flying at 160 miles an hour, and the other plane is flying at 220 miles an hour. How many hours will it be before the planes pass one another? Well, there's their combined distance from one plane to the other at the starting point. And then the first plane is going 160 miles per hour, so we replace the red R with a 160. And the second plane is going at 220 miles per hour, so we replace the blue R sub 1 with a 220. And then their combined distance is stated in the problem as 1,330 miles. And it's implied in this problem that they're starting at the same time, so the times for each plane is the same, so we replace the t sub 1 with a t. And we've now narrowed this down to just one variable, and here's our equation. The distance of the red plane, 160t, plus the distance of the blue plane, 220t, is their combined distance, 1,330 miles. We combine like terms to get 380t equals 1,330, and I suggest a calculator for this one. Divide 1,330 by 380, we get 3.5. Since our rate was in miles per hour, we know that the time is 3.5 hours, or 3.5 hours. And that's the answer to our question. It will take 3.5 hours for the planes to pass each other. And to check your work, I recommend getting out a calculator, type 160 times 3.5 plus 220 times 3.5. You should get 1,330, because I just did. And here's a second type of problem. We have the trains. They're leaving Emerald City at the same time. And the slower train is traveling east at 61 miles an hour, and the faster train is traveling west at 71 miles an hour. And our question, how long before they're 231 miles apart? Well, let's fill in what we know. It's very clear that they left at the same time. So instead of a t and a t sub 1, that variable can be the same. They're both the letter t, because the times are the same for each train. The slower train is 61 for its rate, and the faster train is 71 for its rate. So once again, we just have the one variable t, and their distance is 231 miles. So we add the 71t plus the 61t to get 231. We combine like terms to get 132t. We divide 231 divided by 132, we get 1.75. And once again, we're dealing with miles per hour. So that's 1.75 hours, or if you like, 1 hour and 45 minutes. Just remember, if you want to express it in hours and minutes, don't make the mistake of writing 1 hour and 75 minutes. 0.75 hours is 3/4 of an hour, and that's 45 minutes. So you can write it either way, but our answer is either 1.75 hours or 1 hour and 45 minutes. And once again, you can take the 1.75, substitute it in for t in the original equation, and check it out to make sure that 71t plus 61t is equal to 231. I've checked mine. I hope you'll check yours. And our final problem in this lesson, a car left Central City traveling east at an average speed of 32 miles an hour. 15 minutes later, another car left Central City, also traveling east at an average speed of 48 miles per hour. How long will it take the second car to catch up to the first car? And in this case, their distances are the same. And now we can fill in 32 miles per hour for the rate of the first car, 48 miles per hour for the rate of the second car. But in this case, the times are different. But we want one variable. So since the first car had a 15-minute head start, we'll do a little mental arithmetic. 15 minutes is 1/4 of an hour, or 0.25 hours. So we put t plus 0.25 in parentheses to represent the time of the first car that had the head start. The second car can just be t. And that'll answer our question, because the question is, how long will it take the second car to catch up to the first car? So we can find out a value for t that will answer our question. Well, the distances are the same. So instead of these two rate times times adding up to a number, they're equal to one another. So here's our equation. In fact, we don't even know what the distance is. But we know that the rate times the time of the red car is equal to the rate times the time of the blue car. And now we apply the distributive property to get 32t plus 8 is equal to 48t. We subtract 32t from both sides to get that 8 is equal to 16t. We divide both sides by 16 and get that t is 0.5, or 1/2 hour. And that will answer our question. It'll take a half hour, or if you like, 0.5 hours, or even 30 minutes for the second car to catch up to the first car. But sometimes these problems have different questions. And here's an alternate question that might be in a problem such as this one. How far will each car have traveled? Well, if we can answer this question, we'll also be able to check our work for the original problem. First, we look back at our notes to get what we wrote as an answer for the first problem, that it would take a half hour for the second car to catch up to the first car. Then we look at our expressions for the rate times the time of each car, and we got that off of our original notes. And now we plug in 0.5 for t. So for the first car, it's 32 times the quantity 0.5 plus 0.25, which is 32 times 0.75, which is 24. And for the second car, it's a little quicker. 48 times 0.5 is 24. They check out, they're equal, and each car has traveled 24 miles. Many rate, time, and distance problems involve things traveling towards each other. Others involve things traveling away from each other in opposite directions. A third type of problem involves one thing starting first, so another thing needs to catch up. In general, make one unknown quantity equal to a variable, and then express the other unknown quantities in terms of that variable. And always remember, rate times time equals distance.